Chapter 3, Motion in a Straight Line. Now, motion is common to everything in the universe. We walk, we run, and ride a bicycle. Now, even when we are sleeping, air moves into and out of our lungs. And blood also flows in arteries and veins inside our body. We see leaves falling from trees and water flowing down a dam. Now, vehicles and airplanes carry people from one place to another. Now, even the earth also is not stationary. It's moving, it's rotating once every 24 hours. Not just rotating about its axis, it also revolves around the sun once in a year. The sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. So everything around us seems to be in motion. So what is motion? Now, motion is a change in position of an object with time. Now, in this chapter, we shall learn how to describe motion. And motion can be described under the three headings, which is number 1, kinematics. Then number 2, dynamics. And number 3, statics. So these three headings, kinematics, dynamics and statics, they are a branch of physics. Okay, they are a subtopic of a branch of physics known as mechanics. And mechanics is a branch of physics which studies motion. Now, kinematics, in this heading we shall study about motion without taking into account the cause of motion. And in dynamics, we shall study motion taking into account the cause of motion. And most of the time, what causes motion is a force. Suppose this object here, it will be stationary unless I give it a push or unless I give it a pull. Then only this object will be in motion. So, under this dynamics, we shall study about the cause of motion, which is the force. And under statics, we shall study motion which have a zero acceleration. And most of the time in statics, the force, they are in equilibrium. Okay, so the motion is a constant, uniform, accelerated motion. Now, under kinematics, we shall learn about displacement, velocity, and acceleration. These are the three quantities, physical quantity, which you can use to describe. So these are the three quantities which you can use to describe motion. So we have displacement, usually denoted by S, or distance, or even path length, and velocity, usually denoted by V or U for initial velocity, and acceleration, usually denoted by A. So under kinematics, we shall study these three physical quantities: displacement, velocity, and acceleration. Okay, so displacement will tell you how we displace one object from one position to another. Velocity will tell you how fast that object is moving from one point to another. And acceleration will tell you how much is the change in velocity during that time interval from one position to, as the object moves from one position to another position. Now in this chapter 3, we will study motion in a straight line. And this is also known as rectilinear motion or motion in one dimension. And while studying motion, we'll have to consider any object as a point object. And this assumption is true only if that object is very small as compared to the distance which it is moving. For example, if a car is moving from one city to another, then that car is taken to be a point object. For example, I'll give you suppose you are in Shillong city, and if you want to travel from Shillong city to Guwahati city in a car, then that car will be denoted as a point, a blue dot on the Google map. So that point is a point object of the car in which you are traveling. So remember that most of the objects will be taken as a point object. So far as the distance which it moves is much more larger than the dimensions of that object. So motion is a straight line, is a motion which this object, this point object, is moving in one dimension, either to this in this direction, or in this direction, or in this direction, or in this direction. So this is a straight line. Okay, so it can move from left to right, okay, in this direction and this direction, or it can move up and down, or north and south, or it can move in this direction and in this direction. So this motion is considered the motion in a straight line, okay, or motion in one dimension. Now most of the objects you see, they are moving in a three-dimensional space. Okay, and for example, like this object now here, which you are seeing in video, this is moving in a two-dimensional coordinate system. But for point object, for example, a ball bouncing up and down, that is considered a motion in one dimension. Or if a spring which is oscillating left and right, that is considered as motion in one dimension, or motion in a straight line. Now motion is change in the position of an object with time. So in order to specify this position, we shall use a reference point and a set of axes. For example, if your object is moving in a straight line, say from this position, it's moving from this position to this position. So this is moving in a straight line. So if your object moves from this position to this position, then to specify this position, we shall use a reference point O and a set of coordinate axes, which in this case is the x-axis. So here we can specify the position. If your object is at this position, then the position will be x1, and at this position the object is at x2. So in order to specify motion in one dimension, we shall use this x-axis, a reference point, and the x-axis. We can also use the y-axis, okay, and the z-axis to specify one dimension. But whenever your object is moving in a straight line, only one coordinate axis is required to specify the position. Okay, if it's moving up and down, you can use the y-axis. If it's moving in this direction, then you can use the z-axis. Now if your object is moving in a plane, for example the carom board dice or the billiard balls, they are moving on the board, isn't it? So to specify the position of those objects, for example the carom dice moving on the board, we shall make use of two coordinate axes. Suppose your carom dice is at this position, it's moving from this position to this position. Then in order to specify this motion, we shall use two coordinate axes and a reference point. So this is the reference point, so we use x coordinate axis and the y coordinate axis. So when your object is at this position, you can denote it as x1, y1, and when your object is at this position, we can write this position as x2, y2. So your object is changing from x1, y1 to x2, y2. Okay, it can move in a straight line, it can also move in a curve, for example a projectile motion. If we take example of a projectile motion, if we throw anything in space and that object is under influence of gravity, then that is known as a projectile. For example, if you shoot a javelin throw or a shot put, then that shot put will be moving in a curve, and that motion can be described by using the two coordinate axes x and y. So that if the shot put is at this position, you can have x and y coordinate system to describe that object at this position. Now if we take for example another type of motion, suppose birds moving from one position, okay, migrating from one position to another. Now birds, they are moving in a three-dimensional space, in space. So in order to specify the motion of the birds moving from one position to another position, we shall make use of three coordinate axes: the x-axis, the y-axis, and the z-axis. So this three axis, x, y, and z-axis, this will specify the position of the object, which is the case in which is the bird in the space. So if the object is moving in space, say from one position to another position, then to specify this position, we'll have to use the x, the y, and the z-axis. So if we use the y-axis, first we'll use the z-axis. So this is the z-axis. You see objects at this position. So the z-axis will be this one. This will represent the z-axis. This line which is parallel to the x-axis will represent the x-axis. And this line here will represent the y-axis because it's parallel to the y-axis. So here this position is described by x1, y1, and z1. x1, y1, and z1. So this is z1. This will be x1. Okay, so from here to here, here to here, this is z1, and from this point to this point is x1. So from this point to this point is x1, and from this point to this point is y1. So from here to here, here to here, this is y1. Similarly for this object also, it will move from here to here. Then this position is described by x2, y2, and z2. So in order to specify the position of an object, we will make use of a reference point and the coordinate axis. If your object is moving in a straight line, we just need only one coordinate axis. If your object is moving in a plane, then we make use of two coordinate axes, and if your object is moving in space, then we shall make use of three coordinate axes. So this coordinate system, okay, the x, the y and the z axis, along with a clock, constitute a frame of reference. Okay, so for example, the object changes its position with time. Okay, from this point to this, from this position to this position with time. So if we have this position with a clock, then this coordinate system along with the clock will constitute a frame. It's known as a frame of reference. If we have only one axis also, if we have one axis and a clock, that will constitute a frame of reference. We have two axes with a clock, constitute a frame of reference, and the z-axis with a clock with a time will constitute the frame of reference. Okay, so we shall draw this frame of reference, okay, in the next topic in this way. Suppose this is your frame of this is the coordinate axis, and this will be the time axis. So this will constitute the frame of reference. So in this chapter we shall use only one coordinate axis, since we're dealing with motion in one dimension. If we have two axes, it's known as motion in two dimension. If we have three axes, then it's known as motion in three dimension or 3D. So in this chapter we shall only consider motion in one dimension. So we'll only make use of the one axis, x-axis or the y-axis. So if it's moving left, right, forward, backward, we use one coordinate axis, which is the x-axis. If it moves up, down, we will use the y-axis. Now we shall come to the concept of path length. Now we consider, say, the motion of a car which is moving in a straight line. So in order to specify or to describe this motion, we shall make use of a coordinate axis, x-axis, and a reference point, such that the x-axis, it coincides with the path of the car's motion. Okay, so here we are using the x-axis. This is the reference point, and see the positions to the right of the reference point is taken as positive, and position to the left, this one, is taken as negative. So here we have in this direction it's taken as negative, and we have minus 40, then we have minus 80, then minus 120, then minus 160. Then in this direction we have 40, we have 80, then we have 120, 160, then 200, then 240, then 280, 320, then 360, and 400. So in this direction it's positive, in this direction it's negative. Now suppose the car is moving from one position, say it starts at O. So if the car starts at O and it moves to this position P. So from this position O to this position P, the distance traveled by this car is the path length, and in this case your path length will be equal to 360 meters. Okay, so here this is in meters. So the path length is the distance, okay, the distance in which an object travels from one position to another position. Now we consider another case in which your object moves, say, from P, from this position P to Q. So it moves from P to Q. Then in this case, what will be the distance in which it moves from P to Q? 360, and we have 240. So from here to here, okay, from this will be the path length. Okay, so if it moves from P, from this position to this position, the path length will be this one. And you can calculate it by taking the difference of 360 and this 240, in which you'll get the path length to be equal to 120 meter. So from O to P, the path length is 360, 0 to 360, and from P to Q, the path length is 120. You can see that the path length does not depend upon the direction in which the car is moving. It's moving in this direction or in this direction, it doesn't matter. You just need to take the difference or the distance between the 2 points in which the car travels from. Now if the car travels from O to P, then again from P to Q, then the total path length in this case will be the sum of 360 and 120. So if it moves from O to P, then from P to Q, then the path length will be equal to, the sum of this will be 480 meter. So that is the concept of path length. It's just the distance between 2 points in which that object is moving. So if it's moving from one position to another position, you just need to take the distance in which the object moves. Now the concept of displacement is different from the concept of path length, in that displacement has got a direction and magnitude. Okay, so again we shall take the same example of a car moving in a straight line. Suppose at any position, at any time, the car will be at, say at this position, x1. Suppose at t1, at time t1, the car is at this position, x1. Then after some time, say after t2 or at t2, the car is at this position. So the car is moving from this position to this position. Then the displacement of this car is the change in position, and it is denoted by delta. This is a Greek letter, delta x, and this is equal to the final position x2 minus the initial position. So remember, we have to first write the final position, then minus the initial position. So the initial position will be at x1 and the final position will be at x2. So in this case, if it's moving from this position 80 to this position 240 meter, then the displacement in this case, delta x, will be equal to 240 minus 80, and this is equal to, you take the difference of this one, you get 160 meter. So the displacement from this position x1 to this position x2 is equal to 160 meter, and in this case it is a positive displacement. And see, this displacement, it can also be negative. Now for example, if the car is moving from this position, okay, if it's moving from this position 240 to this position, so if it's moving, instead of moving in this direction, it moves in the opposite direction. So it's moving in the opposite direction. Then the initial position is taken to be this one, x1, and the final position is taken to be this, x2. So it's moving from this position to this position. In that case, the displacement will be given as the final position 80 minus the initial position 240 meter. And in this case, if you take the difference, you will get minus 160 meter. And as you can see here, this is a negative. So your displacement, it can be positive, it can also be negative, depending upon the direction in which it is moving. If it is moving in this direction, in the negative x direction, then the displacement is negative, and if it's moving in this direction, the positive x direction, then the displacement is positive. So depending upon the value of this initial position and final position, delta x can be positive or it can be negative. And in this case, you can see x2 80 is less than x1, which is 240. In the earlier case, what we have is x2 to be 240 and x1 to be 80. And in the earlier case, your x2 is greater than x1. So we can write this in this formula. If x2 is greater than x1, then your delta x is positive, and if x2 is less than x1, then your delta x is negative. So your displacement, it can be positive, it can be negative. It can also be zero. Displacement can also have a zero value. Unlike path length cannot have a zero value. Displacement can have a zero value. And path length also cannot have a negative value, but displacement can have a negative value. Now if you take the path length in this case, just take the distance from here to here, which is 160. Okay, just measure the distance from here to here. But if you take the distance, you'll have to take into account the direction of the motion of the object. If it's moving in this direction, then it will be negative. If it's moving in this direction, then it will be a positive. Even if your object is moving up and down, suppose if your object is moving up, then suppose your object is moving upwards, then this direction is taken to be positive, and if it is moving downwards, then this direction is taken to be negative. So in this direction, if it moves to the right, positive. If it moves to the left, then negative. Okay, so displacement has got a magnitude as well as direction. Hence, we call displacement as a vector quantity. Okay, displacement is a vector quantity. It has magnitude and direction. Now, with vector, we will study in the next chapter. In this chapter, we shall consider object which is moving in this direction to be positive, in this direction to be positive, in this direction to be negative, and in this direction to be negative. Okay, so displacement can also be zero. That I can show you by an example. Suppose now a car is moving from O, from this position, say to this position P. So it's moving in this direction. Then again from P to O. So it's moving like this. Okay, so your car is moving in this direction. Then again it goes back to its initial position. So here, what is the initial position? This will be the initial position, x1. Then again, what will be the final position? The final position also will be the same. So here we have x2. So in this case, the displacement will be equal to 0. So if it starts from the initial position, it returns back to the initial position, then we say that the displacement is 0. So here you can see if x2, you can add another formula here. If x2 is equal to x1, then the delta x is equal to 0. So displacement can have positive, negative and 0. Okay, now path length. Now path length is always positive. Alright, and the path length is taken to be the magnitude of the displacement. So here in this case, if it moves from O to P, P to Q, the displacement is 0, but the path length is not equal to 0. The path length will be 0 to 240, so this will be the distance, first distance, then again 240 to 0, then the distance or the path length in this case will be equal to path length, this will be equal to 240 for 0 to P, then plus, what is the distance again from 0 to P? From P to O? 240, so 240 again. So the path length will be equal to 480 meter. So you can see that even if the displacement is 0, but the path length is not equal to 0, it's equal to 480 meter. And okay, so even here also, if it's negative, the path length is positive. Now the motion of an object can be represented by a position time graph, or we call this position time graph a frame of reference. For example, your object is moving, say, in the positive x direction, starting from the initial position or the frame of reference, or the point, I mean the reference point O. Then it moves to this position, 10 meter, then it moves to 20 meter, then it moves to 30 meter, then it moves to 40 meter, then it can move to 50 meter. So this is the x-axis. So suppose at t is equal to 0, your object is at this position. So I'll write here t is equal to 0, your object is at this position. Then at t1, your object will be at this position. Then at t2, the object is at this position. So at t3, object is at this position. At t4, object is at this position, and after some time t5, object reach this position. Or what I can do is, instead of just t1, t2, I can write with the time itself. So suppose at 0 second is at O, at 5 second it is at 10 meter, at 10 second it is at 20, at 15 second it is at 30, at 20 second the object is at this position, 40, and at 25 second the object is at this position. So in the time interval from 0 to 25 seconds, the object travels a distance of 50 meter, and it is displaced from 0 to 50 meter. So this motion of the object along the x-axis with the time is known as the frame of reference, and we can draw this frame of reference as, so you can draw the x-axis in this direction. Don't be confused with the y-axis. This is the x-axis, and the time is taken to be in this direction. So this is the starting point. So at O, so I'll first draw the scale. We have 5, 10 second, 15 second, 20 second, and 25 second. Then again we have here also 10, then we have 20, 30, 40, 50. So we have 10 meter, then we have 20 meter, 30 meter, 40 meter, and 50 meter. So this is known as the frame of reference, or the position xt graph, position time graph. Okay, we call this as the position time graph. So here at 5 seconds, so this is in second, this is in meter. So at 5 seconds, where's your object? At 10 meters, so your object is here. Then at 10 seconds, where's your object? At 20. So you can describe that to be here. And at 15 seconds, your object is at this position. At 20 seconds, your object is at 40. So the position time graph will be here. Then at 25 seconds, your object is at 50. So the position time graph will be here. So 5 seconds is at 10, 10 seconds is at 20, 15 seconds is at 30 meter, 20 seconds it is at 40 meter, 25 seconds it is at 50 meter. So this, if you join all these points, then this line is known as the position time graph, and in this case you can see it is a straight line. Okay, it is a straight line passing through the origin, and this is an indicator of a uniform motion. From this line, okay, we conclude that the motion is a uniform motion. Now, what is a uniform motion? Uniform motion, okay, is an object moving along a straight line, okay, which covers equal distance in equal interval of time. So you can see in this interval, in 5 seconds, how much does it cover? 10 meter. Then from here to here, what is the interval? From 5 to 10, the interval will be 10 minus 5, which is 5 seconds, and the distance will be 20 minus 10, which is 10 a meter. So here again, in 5 seconds it travels 10 meter, and similarly here also, in 5 seconds it travels 10 meter, in 5 seconds it travels 10 meter, in 5 seconds it travels 10 meter. So an object is said to be in a uniform motion if it covers equal distance, see 10, 10, 10, 10, 10, in equal intervals of time, 5, 5, 5, 5, 5. So this is a uniform motion. So from this graph we say that the object is in uniform motion. Now what if the object is at rest? It's not moving. Then how will you specify that object which is at rest in the position time graph? The position time graph for the object which is at rest can be specified by a straight line which is parallel to the time axis. Suppose the object is not in motion. Right, suppose the object is always at this time. Always at this position. See, at P position. So it's not moving, it's always stationary. So if even if your time it's moving, after 5, 10, 15, 20, 25, the object will always be at this position. So in order to draw that position time graph for the object which is at rest, we simply draw a parallel line which is parallel to the time axis. Then this will indicate that the object is at rest. It is not changing its position. Hence, it is at rest. So that is the concept of path length, displacement, and the frame of reference, or the position time graph. In the next lecture video, I'll explain to you another quantity which you can use to describe motion, which is velocity and acceleration. Then we shall relate all these quantities: displacement, velocity, and acceleration. There's an equation which relate all the quantities, okay, which is known as the equation of motion, and that we'll have to derive.